So there's this classic story about a well-known scientist who is giving a public lecture on astronomy. He's up there describing how the Earth orbits the Sun and how the Sun orbits the center of our vast galaxy. Really laying out the grand mechanics of the cosmos. But at the very end, this little old lady at the back of the room stands up and says, "What you have told us is absolute rubbish. The world is really just a flat plate supported on the back of a giant tortoise." The scientist, probably giving a bit of a superior smile, asks her, "Okay, but what is the tortoise standing on?" And without missing a beat, the old lady replies, "You're very clever, young man, but it's turtles all the way down." Okay, let's dive right into this explainer, because honestly, as ridiculous as a towering stack of turtles sounds, we have to ask ourselves, do we actually know any better?
Welcome to the Day's Explainer. We're exploring the work of one of the absolute most brilliant minds of our era and his monumental quest to answer humanity's biggest, most profound questions. We're talking, of course, about Stephen Hawking and his masterpiece, A Brief History of Time. Where did we come from? What is the universe actually made of? Did time have a beginning? And, maybe more frighteningly, will it have an end? Today, we are going to trace the breathtaking evolution of how we understand the cosmos, and we're going to break down some incredibly complex physics into fascinating, completely accessible ideas.
Here's a quick roadmap for our journey today. First, our shifting cosmic picture. Then, relativistic space and time. Third, the expanding universe. Fourth, the uncertainty principle. Fifth, quarks and cosmic forces. And finally, number 6, the unified theory quest. We're going to zoom all the way out to the galaxies and then all the way down into the invisible quantum realm.
All right, let's kick things off with Section 1, our shifting cosmic picture.
Think about it. For a very long time, humanity viewed the heavens as totally fixed, perfect, and static. And naturally, we thought we were sitting comfortably right at the center of it all. It really kind of maps our changing ego as a species. Way back in 340 BC, Aristotle argued for an Earth-centric universe. Ptolemy later elaborated that into this complex model of perfect spheres orbiting the Earth. It actually wasn't until 1514 that Nicholas Copernicus dared to suggest that the Sun was stationary at the center. And he actually did this anonymously at first, out of a very real fear of being branded a heretic. But the real death blow to that old Earth-centric view came in 1687, when Sir Isaac Newton published his laws of universal gravitation. Suddenly, we weren't looking at these mystical, perfect circles anymore. We were looking at a dynamic, gravity-bound system of elliptical orbits where literally every body in the universe attracts every other body.
Moving right along to Section 2, relativistic space and time.
So Newton's laws were fantastic, right? But as we hit the early 20th century, a completely unknown Swiss patent clerk named Albert Einstein arrives and just shatters our fundamental understanding of reality. See, classical Newtonian physics believed in absolute space and absolute time. Let's do a thought experiment. Imagine you're playing ping pong on a moving train. If you bounce the ball on the table, it hits the exact same spot from your perspective. But to an observer standing outside on the track watching you go by, that ball has traveled 40 meters between bounces because the train is moving. Now, Newton's laws still work perfectly here, which proved there is no absolute standard of rest. But Newton still believed time ticked on reliably, exactly the same for everyone, everywhere. Well, Einstein completely destroyed that idea. He realized that if the speed of light is fixed for everyone, then time and distance must be flexible. Time and space are entirely personal and relative to the observer.
And the real game changer here is the concept of space-time. Einstein didn't just tweak space and time. He literally fused the 3 dimensions of space and the 1 dimension of time into a single dynamic 4-dimensional fabric. And this just brilliantly illustrates his new concept of gravity. Because gravity isn't just some invisible string pulling things together. It is a literal warping of this space-time fabric. Massive bodies, like our Sun, literally curve the space-time around them. So the planets aren't being pulled, they are just following the nearest thing to a straight line along a curved fabric. Space and time are now dynamic players in the universe. They are affected by absolutely everything that happens in it.
Which brings us to Section 3, the expanding universe.
Now that we've totally warped our local space-time, let's shift our scale outward to the galaxies. Up into the 1920s, even Einstein thought the universe was static. But another massive paradigm shift was right around the corner. Let's talk about the Doppler effect and redshift. In 1929, Edwin Hubble observed the spectra of light from distant galaxies and noticed something staggering. Their light was shifted toward the red end of the spectrum. To picture this, think of a passing car. As it drives toward you, the engine pitch sounds really high because the sound waves are being compressed. But as it drives away, the pitch drops lower because those sound waves are stretching out. Well, light works the exact same way.
Because the light from those distant galaxies was stretched out, or redshifted, it meant they were moving away from us. And not only that, but the farther away they were, the faster they were receding.
Watch how this logically builds into an incredible origin story. Step 1. We observe that galaxies are moving apart. The universe is expanding. Okay, so step 2. Let's wind the cosmic clock backward. If everything is moving apart today, it stands to reason that, in the past, things were closer together. If you rewind it far enough, we're talking about 10 to 20,000 million years. You reach step 3, a point where all the matter in the universe converges at exactly the same place. An infinitely dense, infinitely small point called a singularity, the Big Bang. And here's the kicker. At this point of infinite density, all our classical laws of science simply break down.
Now for section 4, the uncertainty principle.
Because those classical physics rules completely break down at the Big Bang, we have to look for a different set of rules. We have to zoom all the way down into the microscopic quantum realm where things get truly, mind-bendingly bizarre. Enter Werner Heisenberg and his incredible 1926 breakthrough. Previously, scientists dreamed of a perfectly deterministic universe. They figured if you knew the position and speed of every single particle, you could predict the entire future of the universe. Simple, right? But Heisenberg proved that you cannot accurately measure both a particle's position and its velocity at the exact same time. Why? Well, because to observe a particle, you have to shine light on it, and a quantum of light contains energy that physically bumps the particle, changing its speed in a totally unpredictable way. Literally, the very act of observing changes the state of reality. And this perfectly illustrates the sheer weirdness of the quantum world, wave-particle duality. Take the famous two-slit experiment. Scientists fired single particles, like electrons, through a barrier that had 2 slits in it. Logically, you'd expect them to land in 2 distinct clumps on the screen behind it, right? But they don't. They create a pattern of interfering fringes, exactly like overlapping ripples on a pond. Even when fired one by one, a single electron behaves like a wave, seemingly passing through both slits at the exact same time and interfering with itself. In this realm, particles just do not have definite paths. They have a range of probabilities.
Let's dig even deeper in section 5, quarks and cosmic forces. If atoms aren't the smallest things in the universe, what is? Let's explore the true building blocks of matter. For a long time, we thought protons and neutrons were the ultimate fundamental particles. But by colliding them at ridiculously high speeds, we realized they're actually made of truly elementary particles called quarks. And you have to love the naming convention physicists went with here. Quarks come in 6 delightfully named flavors: up, down, strange, charmed, bottom, and top. A proton, for instance, is just made of 2 up quarks and 1 down quark. These are the ultimate Legos of our reality. But these building blocks don't just sit there, they interact. And all interactions in the universe fall into 4 fundamental force categories. You have gravity, pulling massive bodies together, the electromagnetic force, holding electrons to nuclei, the weak nuclear force, which is responsible for radioactivity, and the strong nuclear force, holding those tiny quarks together inside protons and neutrons. Amazingly, quantum mechanics tells us these forces are transmitted by an exchange of unseen, virtual force-carrying particles. It's kind of like tiny invisible messengers zooming back and forth, constantly telling matter exactly how to behave.
And that brings us to our final stop, section 6, the unified theory quest. So, when we try to bring the macroscopic spacetime of our first half together with the microscopic quantum weirdness of our second half, we hit the ultimate paradox of our time. We essentially have 2 incredibly successful partial theories. General relativity beautifully explains the massive cosmos, gravity, and the large-scale structure of the universe, and quantum mechanics flawlessly explains the tiny, subatomic world of probabilities and particles. But here is the massive problem and why all of this matters so much. They are completely inconsistent with each other. They literally cannot both be correct. If you try to apply classical general relativity to the infinitely dense singularity of a black hole or the Big Bang, the math just blows up. It stops working. We desperately need a unified theory, a quantum theory of gravity, to finally combine them.
Which leaves us with this final, truly profound question. If we do eventually discover a complete, unified theory of everything, what does it mean for us? Will it mean a return to determinism, proving that absolutely all our actions are just the inevitable results of cosmic equations? Or, as Stephen Hawking himself famously pondered, would finding the ultimate theory of the universe finally allow us to know the mind of God? It is a staggering mystery that we are still unraveling. Thank you so much for learning with us today. Keep your curiosity alive, and we'll see you in the next explainer.